next reference guide we'll be looking at in Unit 4 is a reference guide entry number 3. And reference guide entry number 3 deals with something called mixed and entire radicals. So we haven't heard those terms before. So with that in mind, it's a good place to start by defining what each of those things are. Now, a mixed radical is a radical that includes a number in front of its radical or its root sign. So for example, something like 4 root 3 and something like 22 cubed root 7. Those are examples of mixed radicals. And you haven't seen any of those before. I mean, you may have seen a couple of examples in the textbook or something like that, but we haven't analyzed how we go about determining where that number in front of the radical sign comes from. And that's half of what we're going to be doing in today's reference guide. We'll be looking at radicals and we'll be simplifying them in such a way that we get a value that appears outside of the radical sign, like the 4 and the 22 do in the example that's included there. The second definition in this reference guide is entire radical. And an entire radical is a radical that you should be familiar in seeing. Here we have no number out front of the radical sign. We just have a radical that has an index, a radical sign, and a radicand. So with this, you can see examples like square root of 17, 4 through to 15, and so on. And like I said, those are the types of radicals with which you are already familiar. You've worked with those a little bit. And what we're going to be doing is we're going to be taking mixed radicals and writing them as entire radicals, and vice versa. We're going to be taking entire radicals and looking at the steps necessary to write them as a mixed radical. So we can think of mixed radicals almost as like a simplified or a factored version of an entire radical, and we'll talk more about that as this reference guide moves on. So we'll start by writing a mixed radical, or by writing an entire radical as a mixed radical. And there's two ways you can do this. There is a quick way, which is quite heavy on mental math, and there is a way that you can solve it that involves prime factorization. And if you're wondering where that word comes from, it comes from reference guide 1 of unit 3, reference guides 1, 2, and 3 of that unit, but the first time you see it is in the first reference guide. So we'll look at both methods, and I'll show you both ways to do that, and you can decide which method you like the best. I will never dictate to you how you're meant to solve these problems. I'll show you two ways to do it, and you can choose the one that makes the most sense to you. So if we are using prime factors to come up with a mixed radical, we're going to look at the radicand, or the number under the radical sign. And if it's a perfect square or cube, then we'll just solve it. But you'll notice with these problems, it's not going to be a perfect square or cube anymore. So you're going to get values like square root of 80, values like square root of 105, things like that, where it's not going to work out as perfectly as some of the values that we've seen earlier in this unit have. So the first thing we're going to do is we're going to write the radicand as a product of its prime factors. So we're thinking back to Unit 3, the first 3 reference guides from that unit. Step 2, if it's a perfect square, or if you're finding a square root, you're going to group all pairs together. If you're finding a perfect cube, you're going to group all triples or trios together. So under your radical sign, you're going to write out your prime factors. You're going to group any pairs and any triples together depending on the index of the radical for which you're solving. Step 3, we're going to remove our groups from under the radical sign and place them outside the radical by solving. And that seems a little bit vague just through reading the words, but when you see what that means when we do some examples, it should make sense to you. And then step 4 is to simplify, as it typically is. All right, so let's look at an example. So something like square root of 80. Now, if we were looking at reference guide 2 and placing this on a number line, we would estimate it. We would be able to say that it's really, really close to 9, but it's just a little bit less. But we're not estimating anymore. You're going to see these questions, they say solve. They don't say estimate, they ask you to solve. And when they're saying solve, they're asking you to take it as an entire radical and write it as a mixed radical. So since 80 isn't a perfect square, we run into a bit of an issue. because we don't just know that answer offhand, and we're also being asked to solve. We're not being asked to estimate. So what we can do is we can write out the prime factorization, and I'm just going to do that over here. So you're doing this in your head, but the prime factorization of 80 is pretty easy to come up with. And we find that the prime factorization is 2 to the power of 4 multiplied by 5. And you can see that prime factorization right there. So 2 times 2 times 2 times 2 is 5. And now we put our pairs, since we're finding a square root, we pull out our pairs. Well, we have 2 pairs of 2. So we can think of that as square root of 2 times 2 multiplied by square root of 2 times 2 multiplied by square root of 5. That 5 is just what's left over. It doesn't have anything to pair with. Well, we know square root of 2 times 2 is square root of 4, which is equal to 2. So we're going to have 2 multiplied by 2, and we can't simplify the square root of 5, so that just stays as it is. So we get 4 root 5 as our final answer. Now you can think of it in a different way as well. So if we had a prime factorization of 2 times 2 times 2 times 2 times 5, we can take our pairs, just like we did before, and we can move the number that's in the pair outside the radical sign. So the pair consists of the number 2, so that goes outside the radical sign. And we can write the number of pairs as an exponent. Well, it just so happens to also be 2 this time. And then whatever isn't circled as being part of a pair just remains in the radical, because we can't solve that. And then we just solve 2 squared, which is 4. And we end up with 4 root 5. And that's a really nice way to solve these problems, where we can take the value that's in the pair and move it outside the radical sign. And we can take the number of pairs and write it as an exponent. And then we just have a value to square or cube, depending how many pairs there are. Or maybe there's just one pair and we don't have to do any squaring or cubing. All right, so that's how you would solve this first problem by way of prime factorization. Now it's important to note that you may be asked to solve cube roots in the same way. So something like cube root of 144. And be careful here, because people sometimes just see 144 and they immediately think that the answer is 12. Be careful and make sure that you're looking at the index, because it's cubed root. So there is no number that multiplied by itself 2 times gives us 144, like a cube root asks us to do. So we need to figure it out. And we can use prime factorization to do this. And if we write out our prime factors, we're going to get a much more extensive list. I'll use blue this time so it doesn't blend in. We're going to have a lot of 2's here. And when we write out our prime factorization, we have 4 2's and we have 2 3's. Now what we're being asked to do here is we're being asked to write out our prime factors under the radical sign and to group any triples that exist. So you'll notice that it's 2 times 2 times 2 times 2 times 3 times 3. Well, we do have a triple. We have 3 2's. So we'll write that as cube root of 2 times 2 times 2. And we multiply that by the cube root of 2 times 3 times 3. That's just what's left over. That's what isn't part of a triple. Well, 2 times 2 times 2 is 8. The cube root of 8 is 2. So we get 2 cubed root of 18. But again, we can look at the kind of shorthand version of this even and think of it a different way. So if we go cubed root of 2 multiplied by 2 multiplied by 2 multiplied by 2 multiplied by 3 multiplied by 3, which is just the prime factorization of that value. Well, we have our triple here. So we have 3 2's. And if you remember what we talked about before, you take the number that's in the triple and you move it outside the radical sign. You take the number of triples, well, we just have 1 this time, and you write that as an exponent. So we have one triple consisting of 2's, and we multiply that by the cube root of what's left over. Well, it's 2 times 3 times 3. And then we can just solve that. Well, 2 to the power of 1 is just 2. And then 2 times 3 is 18. So there are two ways that you can solve these problems using prime factorization, and both will get you to the same place, which is nice. Now, as I mentioned before, there is a shorthand method for solving this. The shorthand method for solving this involves a little bit more mental math. So you can use factors, and if you are good at mental math, this is probably the method you'll prefer. So let's look at something like the square root of 32. Well, square root of 32 is not a perfect square. It's somewhere between 5 and 6, a little bit closer to 6. But we're writing it as a mixed radical. Well, the way we can do that is we can think of all the factors of 32, and we can identify the biggest perfect square. So if we recognize in our heads that 16 is a perfect square, and 16 divides into 32, well, rather than writing out the full factor tree and pulling out the prime factors, we can just recognize 16 multiplied by 2 gives us 32. Square root of 16 multiplied by the square root of 2 is the same thing as square root of 16 times 2. And you can see that right here. And then square root of 16 is just 4. So it becomes 4 root 2. And again, if you are fast at mental math, this is probably the method you'll prefer. It involves being able to recognize factors quite easily. But if you're able to do that, then these questions go a little bit faster with this method. It's up to you on which method you prefer. So example number 4, now we're looking at the reverse. We're looking at how to convert a mixed radical into an entire radical, and you'll be responsible for doing both. Well, in order to do this, you have to be able to identify the index of a value. So the first one is 3 square root of 7. Well, we don't write the 2 there, but I am for the purposes of this. So it's 3, and then an index of 2, root 7. And all we're going to do when we solve this is we're going to move the value that's outside the radical underneath, and we're going to write the index as an exponent on that value. So 3 with an index, or with an exponent now of 2, 3 squared multiplied by 7. Well, 3 squared is 9, and 9 multiplied by 7 is 63. So our final answer here is square root of 63. That is 3 root 7 written as an entire radical. And number 5 is the same idea, except now we have a different index. So we start by identifying our index, which is 3. We move the value that was outside the radical sign underneath, and we write the index as its exponent. So it's now cubed root of 5 cubed multiplied by 2. We know 5 cubed to be 125. So our final answer is cube root of 125 multiplied by 2, or cube root of 250. Okay? So when you're converting mixed to entire radicals, you take the number outside the radical sign and move it underneath, and you put the index as its exponent. And then you multiply that value by the radicand, or what was already under the radical sign. Typically, the mixed to entire is something that people find a little bit easier, but again, it's just dependent on the person. So let's look at 2 examples of each, and that will wrap up this reference guide. So at first, we're given entire radicals, and we're asked to write them as mixed. So we can solve this mentally if we want. So if we think of our perfect cube, since it's a cube root, we want to know the biggest perfect cube that divides into 40. Well, the only possible answer there is 8. So we can think of this as cubed root of 8 multiplied by 5, because 8 multiplied by 5 equals 40. This is the same as saying the cubed root of 8 multiplied by the cubed root of 5. So we've pulled out a value that we can simplify. We can simplify cubed root of 8. Cube root of 8, of course, is 2. And then we can't do anything with the cubed root of 5, so that just remains as is. So 2 cubed root 5 would be cubed root of 40 written as a mixed radical. Now I just want to show you this using prime factorization so you can see both ways. So we'll do this in blue. So we can do it that way mentally like we did in red, or we can write out the prime factorization of 40. The prime factorization is 2 multiplied by 2 multiplied by 2 multiplied by 5. So the cube root of 40 is the same as saying the cube root of 2 times 2 times 2 times 5. And now, since it's a cubed root, we are looking for triples. Well, there is a triple. So the number that's involved in the triple is 2. We have one triple, so 2 to the power of 1. And then what's left over is cubed root of 5. So 2 to the power of 1 is just 2, and our final answer is 2 cubed root 5. Okay, and you'll notice that both methods take you to the same answer. One involves mentally being able to work with factors. The other involves being able to utilize your factor trees, your prime factorization, but both bring you to the same answer. So now let's look at cube root of 243. And if space permits, I'll try to do this, or square root, sorry, of 243. And if space permits, I'll try to do this with both methods as well. So maybe mentally, you can quickly identify the biggest perfect square that will divide into 243. And I'll stop at 81 because that's going to be the answer. 81 is the biggest perfect square that divides into 243. And if you can see that mentally, then you can just write it as 81 multiplied by 3, which is the same as square root of 81 multiplied by square root of 3, which gives us a final answer of 9 root 3. That method is fast, but it's also predicated on being able to do mental math effectively. So if mental math is something that you struggle with, or if that method worries you because there's such a heavy reliance on mental math, then you can work with your prime factorization. So 243, it's not going to be quite as easy as 40 to come up with the prime factors of without a calculator, but we can do it. Remember our divisibility rules. So it's not divisible by 2 because it's not an even number, so you move to 3. If the sum of the digits is divisible by 3, then it must also be divisible by 3. Well, 243 is 2 plus 4 plus 3, which is 9, and 9 is divisible by 3. So something is going to go into 243. And maybe you can recognize that's going to be 81, or maybe not. And if not, then you go way back and you divide this out using long division. Well, 3 doesn't go into 2, but it does go into 24 8 times. 8 times 3 is 24. Gives us a remainder of 3. 3 divides into 3 once. So 3 goes into 243 81 times. And at this point, you may recognize that that's 9 times 9. And each of those is 3 multiplied by 3. So 243 as a square root is going to be 3 multiplied by 3 multiplied by 3 multiplied by 3 multiplied by 3. We have 1, 2, 3, 4, and 5. So now we want pairs because it's a square root. There's a pair of 3s. There's a pair of 3s. We have a 3 that's left over with nobody to pair up with, so it will remain under the radical sign. The value of 3 is in the pair, and we have 2 pairs now. And then square root of 3 is left over. So now 3 squared is 9, and we can't do anything with that root 3. So again, we get 9 root 3, which is the same answer that we had last time. Okay, it doesn't matter which method you choose. It's just whichever you are preferring. So now let's look at the reverse. Let's look at mixed to entire. And again, in order to solve these, you have to be able to identify the index. Well, the index of C, it's not written there, it's a square root, so it's implied it has an index of 2. So we're going to move our 5 under the radical sign, and we're going to give it an exponent that's equal to the index of 2, and then we multiply it by the original radicand, which was also 5. Well, 5 squared is 25, and 25 multiplied by 5 is 125. And that's all there is to that. There's no multiple ways to do it. You just move the value outside the radical sign underneath, you make the index an exponent, and you multiply. And our last example we'll look at is 2/4 root of 3. So we're going to move the value that's outside the radical underneath and put the index as its exponent and multiply it by the existing radical. Now it's important to note that the index stays. So it's 4th root in the problem, it's 4th root the whole way through, and it's important not to forget that that index stays. So now we have 4th root of 2 times 2, which is 4, times 2 again, which is 8, times 2 again, which is 16. 2 to the power of 4 constantly comes up. And we end up with 4th root of 16 times 3, or 4th root of 48. Okay, and that reference guide looks at mixed to entire and entire to mixed. It's important to choose the method when going from entire to mixed that you like the best and that you'll find the most success with.